Welcome back, everybody. And I have to apologize for the change of time. And that's mainly because we are interviewing candidates for a local chair of department. And they are giving their talks during our lecture time. So both today and next Thursday, before the Easter break, we are going to anticipate the lecture. So today we're having it from 10:15 to 12 o'clock. And then we have the lab from 2 and on. And next Thursday, we will have the lecture from 12 to 12:15 till 2 o'clock. And then we continue with the lab thereafter. So the topic today is an attempt to wrap up what we started discussing last week about the resampling techniques, and in particular this blocking method. And the blocking method is a method which we are going to present a software for, which you can use in the post-analysis of your data. So the idea is to run a large-scale high-performance computing Monte Carlo calculation, which produces your basic data. And then the basic data is used as an input to these resampling techniques. So that means that you will do a post-analysis after you have performed the standard variational Monte Carlo calculation. And the post-analysis is something which you can always do later. And you should feel free to use the codes which you will find in the lecture notes here. The codes actually for the blocking method, they are based on Marius Jonsen's master thesis. So Marius is actually completing his PhD at Cambridge in the UK. And he actually came across the topic for his master thesis when he was following this specific course. And he was dissatisfied with the original article by Flyberg and Peterson, and he improved upon the proofs for the blocking method and made it much more flexible because the traditional way the blocking method was developed was a method where you actually had to look or study by the eye that the standard deviation did stabilize as a function of the number of blocks. So we are going to go through the basic mathematics of the blocking method, and we are going also to illustrate what kind of results you can get and how you can use the software. So as we mentioned last time, these resampling methods are very important, and they are important because if you think of the experiments and the simulations which are running, you can actually treat them as computer experiments. So in a sense, when you run a variational Monte Carlo calculation or any of these simulations, you should view them as computer experiments. And the results can therefore be analyzed using the same statistical tools which you would use when you analyze experimental data. And the things which we're often using after are the frequency of much often the data occur. We want to calculate expectation values, and we want also to be able to estimate how accurate these values are and potentially find sources for errors. So when you run a Monte Carlo calculation, it's almost a kind of sin not to publish the standard deviation, which you get when you calculate, for example, the energy, the expectation value of the energy. And the type of errors which we end up with are the statistical errors, and those of which we can deal with using tools from statistics. And these resampling methods are actually the kind of tools which we use. And then we have systematic errors, which are much, much more difficult to deal with. And we will not touch upon them, but we will try now with the Hamiltonians which we have to run as decent calculation as possible for the energy, which means to have as many Monte Carlo samples as possible, as is feasible. And then when we have that, we want to estimate the standard deviation and the variance. Now, the thing which we have to deal with in all these calculations is that the data which we will have will exhibit some type of correlations, either because the data or the systems are correlated, and or because the random numbers which we generate are generated by a deterministic algorithm, which means that there will be correlations between the different stochastic events which we simulate with a random number generator. So as you know, the random number generator, they are based on a formula, which in principle are deterministic, but they produce sequences of numbers which obey the requirements for being treated as almost pseudo-random numbers, which means that we can produce a huge set of numbers which are almost independent of each other, but they are not fully independent, which means that there will be some correlations. And that leads us to this statistical quantity, which is called the covariance. And the covariance, when we look at our data and the way we run the calculations, especially when we parallelize the calculations, then the data which we are going to produce will involve the calculation of a double loop over the measurements which we have made. Now, and typically in the type of runs which we make, the number of experiments which we can produce, which is the number of configurations or positions in space which we produce in order to calculate a contribution to the expectation value, these can be in the range of billions, which means that you would have to evaluate a double loop with billions of entries. And you will see that quickly if you run such a calculation, even with 100,000 samples, this is going to take a lot of time to calculate this quantity, even if you do a post-analysis after the calculations. If you were to calculate these things while you run your Monte Carlo code, that would lead to a code which would never end in due time before the deadline for this specific project here. And another thing which we also are going to say something about today is the topic which deals with one-body densities. We're just going to mention how we can calculate them. This is also part of the post-analysis which we can make after we have run the calculation of the energy and found the optimal parameters for the wave function. Then we have the wave function, and then we can use that one to calculate other expectation values. And the one-body densities is a very useful quantity which allows us to say something about the correlations which are induced by the interaction. And in this specific case with the harmonic oscillator, we have an analytical expression for the wave function squared when we don't have an interaction. And then we can see how much the one-body density changes when we add the interaction. And that is a kind of measure of the importance of correlations which are induced due to a two-particle or many-particle interaction. So this is roughly the layout for what we are going to do today. And what I wanted to do first is actually to remind you a little bit of where we were last week. So I'm just going to bring up these equations in order to link that with the discussions of the blocking method and also the Bootstrap method. So let's switch back to the whiteboard and bring back some of the equations and where we ended last week. Okay. So the what we have is typically a set of experiments, and the way we could set this up is to think of a series of experiments. So one of our Monte Carlo calculations can be viewed as one experiment. So if we then think of each experiment, and we give it a label alpha, and each experiment produces then its mean value, and we can also evaluate its variance. So you could think of if you're running in parallel, and if you run 10 parallel calculations, each calculation would then produce its set of observations, and each set of observation would then produce its own variance, and then its own mean value. So hopefully these quantities are independent of calculations which we do or experiments which we do. In principle, they are not. So our main problem is that we, in general, don't know whether this mean value is equal to the exact value if we were to know the statistical distribution which governs the observations which we have. So we would typically run a set of experiments, and this runs over k equal 1 up to n, and we have an x alpha, and this is experiment k for that specific experiment alpha. So observation k for experiment alpha. And in our case, this could then just be one process where we run the calculation for the energy and the variance. And then what we also calculate is the variance for this specific experiment. And in this case, we use the unbiased numbers. If you use NumPy or similar software to calculate the variance, you will see that that's typically written in terms of 1 divided by n minus 1. And that has to do with the fact that we have a biased mean value, which is not equal in principle to the mu exact. And mu exact, if we have a continuous probability, then we have a probability distribution function that is normally given by a domain, an integral of a domain, and then we have a p of x, and then we have x d of x. So we don't know p of x. We're actually making an ansatz for that, which means again that we are not sure when we do the sampling whether we have the exact value. And our probability p of x is actually replaced by this 1 over n, which means that every measurement has the same likelihood, same probability. And you can show them using what's called the law of large numbers from Bernoulli, that this mu of alpha should approach the exact value in the limit n goes to infinity. And the variance is then given by k equal n up to n, and then we have the observation x alpha k minus this mu of alpha, and this is squared. Then what we did next is that we repeat these experiments m times. So I'm just going to set up the equations here for you, which we derived last week. So if we now repeat this m times, we are going to get a sigma of, a mu of m. And this is given by the sum over all the experiments, so the mean values which we had. So this runs now over alpha equal 1 up to the number of experiments we run. And then we have a mu of alpha, and we can rewrite this as a 1 over mn. And then we have a sum of alpha and k, and then we have the single observation alpha k. Now, when we repeat this m times and m becomes a very large number, then the probability which we are approaching, if these are independent and identically distributed observations, then we should approach a Gaussian distribution. So if each of these events, if each x alpha k, the observations we have are what we call in statistics IID, which means that they are independent of each other and identically distributed, then in the limit m goes to infinity, we approach a probability distribution, a probability p of x, which is going to be proportional to e to the minus mu minus x squared divided by 2, and then we have a sigma of m squared here. So that's the Gaussian distribution which we're approaching with a specific mean value mu, which is hopefully then getting as close as possible to the exact value. Now, what we did last week was then to rewrite the variance. So we defined the total variance. And I'm now just going to set up the final expression which we derived last week, and we're not going to go through the derivation of it in order not to annoy you with setting up the same quantities. So the total variance is something which we could rewrite in terms of 1 over m, and then we had n squared and then we have a sum over alpha, the individual experiments, and then we have the sum over k and L equal 1 up to n, and this is a double sum, and then we have x alpha of k minus the expectation value mu of m, and this is multiplied with x alpha of L minus mu of m. So we are assuming that these are independent and identically distributed events and that they have the same mean value. And then we defined also the sample variance of all mn experiments. And then we rewrote the total variance in terms of the sample variance and the so-called covariance. So we just did a rewrite of the equation for the total variance. So the sample variance of all mn experiments, and this is a quantity we get if these experiments are not correlated, then we can actually show that the sample variance, sigma squared, is something which is given by 1 divided by m and n as expected, and we sum over alpha and k, and then we have the x alpha of k minus mu of m, the total mean value, and this is squared. Now, what we did last time was to rewrite this in terms of two quantities, and we rewrote that total variance, sigma m squared, was then rewritten when we took out in the equation which you see here for the total variance. We just split this in the diagonal term with k is equal to L, and then we had the non-diagonal term. And if these events are not correlated, then the non-diagonal term should approach 0 in the limit of an infinity of experiments. So what we would get then is something like this, 1 divided by m of n squared, and then we have a sum over alpha of k. So this is a diagonal piece, and that's given by x alpha k minus mu of m squared. And then we get a term, since we are now summing over only k less than L, we get a factor of 2 then, and this is given by 1 over 2 over mn squared. And then we have a sum over alpha equal 1 up to m, and we have a k less than L and up to n, and then we have an x alpha k minus mu of m, and this is multiplied with x alpha of L minus mu of m. So the last quantity defines actually the covariance. The first quantity is what we call the sample variance of all the mn experiments. So if we now rewrite this in terms of the sample variance, we have this sigma squared divided by n plus what we call the covariance of these quantities x. And the covariance is now given by the equation which we have here. So this is the definition of the covariance for this specific case. So the covariance, as you can also see from these quantities, is also going to be a quantity which is larger than or equal than 0. And that means that if we now leave this type of correlations between the measurements out, then what we are going to get is an over-optimistic determination of the variance. So this quantity here can be proven to be larger than 0 or equal. So which means that if we now don't evaluate the covariance, we may actually get an error, because the standard deviation, which is the standard measure for the error, is given by the square root of the variance, which means that if we don't include the covariance, we may get a too good estimation of the error. So the standard deviation is then calculated from this quantity. Is then given by so normally it's written as STD, and that's simply the square root. So it's sigma divided by the square root of n. Now, normally you will see this with an n minus 1, but we are assuming now that we have so many experiments that you can actually rewrite it as a sigma divided by square root of n. And if this is the case, if now covariance of x is equal to 0. If not, then we are getting a too good estimate of the error. So what we did last time was also to rewrite that quantity in a more compact way. So there is you can rewrite this by defining something which is called a correlation function. And we introduced a shorthand last time of a function which we called f of d. And that function f of d is something which we use to rewrite the covariance term. So we would define that one as an alpha equal 1 up to n here. And then we have a sum from k equal 1 up to n minus this term d. And then we have an x alpha k here minus mu of m. And this is multiplied with x alpha. There's a comma here. And now instead of having the previous variable L, we now have a k plus d minus mu of m. And we can define this quantity d here as the distance between two measurements. So the whole thing with these kind of resampling methods is to establish a distance where we now basically have a covariance which is equal to 0. And when the covariance is equal to 0 as a function of this distance, then we can say that we have reached the correct or the ideal evaluation of the standard deviation. So the whole blocking method, which we are going to introduce pretty soon, is based on us tuning this distance d, so that at the end, we will see a standard deviation which stabilizes as a function of this variable d, which simply means that you have a distance between two observations. The useful way to think of that is that we pick an observation x alpha of k, and you could think of this performed at a time k, and then you perform a new observation at a time k plus d. So this is one way of thinking of this type of correlations. And ideally, you would like these observations to not be correlated, which in statistics translates into a covariance which is identical to 0. So these are the kind of ideal results which we want to achieve, which in turn means that when we rewrite it, now we have a kind of measure for the distance between two types of measurements. Now, if we do that, we could rewrite, and as we did last time, by introducing a function. So we introduced a function which we call the correlation function. And one of the reasons why we do that is that the covariance itself can actually vary a lot. And you can see that clearly from observations which are very different from the mean value. They can actually give you a covariance which is large. So it's common to actually scale this in terms of the variance. So we have a correlation function k of d, which is given by this function f of d, divided by this sample variance which we have. So this is just a way to rewrite the equations. So if I look at this quantity f of 0, d equal to 0, that means that what we have then is simply the diagonal term of the total variance, and that is given by what we previously defined as the sigma squared. So if you look at f of 0, this is simply alpha equal to 1 up to the number of experiments, and then I have a k equal 1 up to n because d is 0, and then I get simply x alpha k minus mu of m squared. And that quantity here is simply sigma squared. So that means that this function k of 0 is equal to 1. And ideally, what we want is that this function k of d, or d different from 0, should be equal to 0. But that's not going to happen. So what you would typically see when you plot it, as we did last time, is that you get something which looks like this as a function of this quantity d. So when we have d equal to 0, then we have 1. So that's a very useful test of the machinery which we have. So this is K of D. And then this is the first observation. And ideally, we would like now for all the other observations that this quantity goes immediately to zero. But what you're going to notice is something which is going to look like this. So you have one observation here, then you may get something here, and then it starts stabilizing, and then it gets closer and closer to zero. And ideally, after a specific distance, it goes exactly to zero. Unfortunately, what you're going to see, even if you do this for a simple test, is actually to run this for the random number generator. And this test of calculating this correlation function is actually one of the tests which is included in order to discriminate whether your random number generator is one which generates long-term correlations or not. So the quicker the random number generator and its correlation function goes to zero, the better the random number generator. But in general, you will have some set of correlations here. And when you then rewrite this quantity here, sigma m, you can rewrite this now in terms of sigma squared divided by n. And then I would have a term which is 2 divided by n. So I'm just taking the sum and rewrite that in terms of this quantity n minus 1 of f of d. So this is just a rewrite of the total quantity we have. And you can rewrite this now as a sigma squared divided by n. And then you have 1 plus 2, and then we have an alpha equal to 1. And this goes over, no, sorry, d. This is a d of up to n minus 1. And then we have this function k of d. Now, what this blocking method deals with is a way to estimate this quantity here without having to calculate a double loop. So what we're going to see now is that we can give an estimate of that quantity without calculating the double loop. And the traditional approach, which was used by Flyvbjerg and Petersen, is as follows. So there's a paper which was introduced by these two Danes, and Flyvbjerg and Petersen. So I invite you to take a look at the original article. So this is a paper which was published in the Journal of Chemical Physics. And this is volume 91. It's back to 1989. So it's not that much used as the Bootstrap method, which we mentioned last week. And the reason for that is that many of the applications of these methods, they are tailored to data sets where you have millions or even billions of observations. And this is where this method has its strength. And we are coming back to that when we revisit the blocking method. And the ideal here was actually to be able to calculate this standard deviation or the variance as a function of these so-called blocks. And we are going to define them just in a while here. They are not that different from this quantity d. And then you will actually see that there's a relation between this quantity d and the number of blocks which we have. So the blocks are actually us dividing the data set in two for each number which you have along the x-axis here. So 0 here means that you take the full data set. And what you're estimating then is actually this sigma squared m. So when you have 0 here, you don't calculate the covariance. So for 0, you would get a result which is given by sigma squared divided by n. So this is this number here. Now then, you keep adding estimations of the covariance without calculating the double loop. So this is estimate. I'm just going to put this up here, and you will see it from the equations below here how this actually comes through. So estimate the covariance without the pain of a double loop. And what you're going to see then, when we now perform these calculations, is that when you recalculate in terms of the number of blocks, as we're going to see from the equations here, and that can be related to this quantity V, which I put up, you will see something which looks like this. And then at a certain point, it stabilizes. And when it stabilizes, that's when you have obtained the ideal value for the standard deviation and the variance. Now, this sounds a little bit strange. Why do we put all this emphasis on this type of calculations here? And why have people devoted so much time to it? Now, there are many answers to that question. So I just wanted to give you the kind of overarching view here. So one argument, which is very important, is that you cannot present results of a stochastic calculation without a proper estimation of the error, period. You can't escape that. If you submit a scientific article or you present a thesis without an error estimation of your statistical observations, you will actually get things immediately back. So that's point one. And we have the tools by which we can estimate these errors. The other thing is that if we don't take into account the covariance, because there may be correlations in the data sets, and we don't know how these correlations actually appear and how they behave, that means that we could, in principle, if we have few observations, we could actually calculate the covariance and simply perform the double loop. But you will quickly see that when you have more than 10,000 or 100,000 experiments, if you have 100,000, you would have to perform 100,000 squared floating point operations in order to get the estimate of the covariance. And that's going clearly to slow down things, in particular, since we are generating millions or even billions of data. So a standard variation Monte Carlo calculation, when you run things in parallel for systems like the ones we are looking at, you would typically generate, if you have access to high performance computing facilities, you would typically generate billions of data. And there's no way you're going to calculate a double loop with billions of data. So that means that you want a reliable estimate. And what Flyvberg and Peterson actually showed is that by their recipe, you will be able to approximate the true estimate of the variance by simply splitting the results into blocks, which are equally sized. So every time when you perform this operation here, you divide your data set in blocks of 2. So you have 2 data sets here. Then here you have actually split it into 4 data sets. You continue on here, you have 8 data sets. So which means that you will often see these calculations being run with 2 to the power of something number of observations. And you will see that in the codes which we're going to present after the break here. So the basic philosophy of this method is to calculate the, or give an estimate of the covariance without calculating the double loop. So it doesn't sound that exciting, but it's going to give us a very good estimate of the standard deviation. Now, the other method which we discussed last week was this Bootstrap method. Now, the Bootstrap method is okay if you're dealing with up to, let's say, something like 10,000 or 100,000 data points. But when you start having much more data, then it really slows down because you are performing bootstraps of the data set you have. So typically, if you have 10,000 entries, you could do something like 1,000 resamplings, which means that you reshuffle your numbers with replacement. It means also that you can pick the same number. So the bootstrap method is extremely simple to implement, but it becomes inefficient numerically when you have many data points. So let me just rewrite this statement, which we also discussed last week. So the bootstrap, which is widely used. So the bootstrap, let me just write this down here. So the bootstrap is typically used with smaller samples, which is often the normal situation. And these are typically very costly samples. So if you run an experiment and you survey, let's say, patients for cancer research, and you would typically survey, let's say, 10,000 patients over, let's say, 10 years. This is a data set which you have. And it's very difficult to increase that data set or repeat the experiments for another 10 years. You don't want to wait another 10 years before you want to publish your results. You have even longer time series, which span over 30, 40 years, where people have surveyed tens of thousands of patients concerning heart diseases and other factors like diabetes and so on. But this is normally used with a smaller sample. And the sample which you would have then would contain a set of observations, x1, x2, up to some x of n. And what you would typically do then is to resample the data. So the new sample is then a resampling of this data. So you reshuffle the data randomly. So that means that you produce a new sample x, and that is given by new numbers x1, x2, and they are taken from the same data set, and they are taken with replacement, which means that you can actually have an x1 prime and x2 prime, which could be the same numbers. And then you repeat this b times the number of bootstraps. And if you do that as many times as you have data sets, which many practitioners often do, then this becomes really expensive from a computational point of view. So with large samples, it becomes expensive and time consuming. So this is with respect of number of floating point operations, flops, and time consuming. Now, the resampling techniques like Bootstrap, they also have another scope, and the other scope is actually to regenerate new data sets without having to rerun the experiment. And you can actually show statistically that if you have independent and identically distributed stochastic events, then these calculations of mean values with these resampled data sets and also the variance, they do actually approach the true variance and the true mean value. So this can actually be proven if you have independent and identical distributed events. But for us, this becomes less practical when we're now going to do the resampling. So if we now look at the blocking method, the way it was introduced by Flyvbjerg and Petersen, so let's now just look back at the equations which we had. So we rewrote the sample variance, the total variance, sorry, in terms of this correlation function, which depends on the distance between two observations. And this was essentially what Flyvbjerg and Petersen started with. So let's take a look at the blocking method and go through the algorithm and the computational details behind it. So here I'm actually going to follow the article by Flyvbjerg and Petersen. So what they started with is to define the mean value as we have done before. So we would have a sum over I equal 1 up to n of x of I. We would have a expectation value for the variance with this mu here, which is simply the expectation value of x squared. So this sign E with a bar on the side there is meant to be my indication that this is an expectation value minus mu squared. And we know that when we have m equal to 1, so let's just rewrite that and go back to our expression with sigma m squared and just write it as so if we put m equal to 1, we have one big observation here. This is given by this quantity sigma squared divided by n plus 2 divided by n squared. And then we have the sum over k less than L. So this is the covariance. And this is our xk minus mu and multiplied with xl minus mu here. So I'm just simplifying the expressions which I put up just some few moments ago. And I put this m equal to 1. So we just have a huge set of data, n here. And when we do that, I'm just going to label this as a sigma squared of mu. This is what I will mean with that. So what the Flyvbjerg and Petersen did was to introduce another variable instead of the f, which I had. But this is supposed to be the same as the f, which I have. And this is the expectation value. So this is actually the covariance of xi, xj minus e, and this is the mean value squared. So this is actually our mean value squared. And then they label this as a gamma of t. And where this t is the distance between two measurements. So what I'm doing now is to relate the equation which I put up with the equations which you will find in the article of Flyvbjerg and Petersen. Now, with that, they could then rewrite the equation for the standard deviation, where they define gamma 0 as sigma squared, the same quantity which we had in the original equation. And then you can rewrite this sigma squared of mu in terms of 1 over n squared. And this has a double sum ij of gamma ij. This is the basic equations they have in their analysis. And this is now given by a sum where we have now gamma 0, which plays the same role as our sigma squared, plus 2 divided by n here. Oops, sorry. And 2 divided by n, and then there should be, no, the n doesn't come there. The n, so it's a factor of 2 here, if I remember correctly. And then I have a sum over t equal to 1 of n minus 1 and 1 minus t divided by n multiplied with this quantity gamma of t here. And this quantity which you see here plays the same role as this function which I had, which was given as a sum over d up to n minus 1 of this quantity f of d. So this is just their rewrite of the same quantity. So the basic algorithm, which they presented back in '89, is to split the data in chunks of 2 each time, and then just keep repeating that. So this is to transform the data. And then after I've written down this one, we're going to take a small break. So transform the data sets, which we have. X. So these are our observations, x1, x2, up to some x of n, into half as large data sets. So that means that we get a new data set, which should contain the same data points, but it has been split now into x1 prime and x2 prime, x3 prime, and this goes up to an xn prime and primed, where this n primed is simply a half times n. And it means also that this data set x of I prime is now given by the original data set, which is x2i minus 1 plus x2 of I. So the data set now is simply, you just split it in chunks of 2. And the hope then is that you can, with these different chunks of data, is that you can demonstrate that the standard deviation stabilizes as a function of these blocks, which means that we have found a set of blocks where the data can be considered as almost independent of the data from the previous block. So by looking at how the standard deviation or the variance stabilizes as a function of this splitting in two iteratively, the hope then is that you will have a variance which stabilizes and just converges to a specific value. And the whole recipe, you can actually show that, and we will see this after the break, is a recipe where you are slowly converging towards the correct value for the covariance. And this is going to be a cheap way by which we can evaluate the covariance without calculating a double loop. This sounds extremely exciting, doesn't it? So we have just been doing all this just to avoid to evaluate a double loop. Okay, guys, we are past the hour, so let's take a small break. So I'm going to pause the recording here. So what Flyvbjerg and Petersen did was to rewrite the same equations which I discussed previously in terms of the total variance, which is given by the sample variance plus the covariance. And this covariance is the one which includes the correlations between the different stochastic events. And if we have independent and identically distributed events, then the covariance should be exactly equal to 0. So unfortunately, we don't know whether we have that. So we need to give an estimate of the covariance in order to have a reliable estimate of the standard deviation and the error which we produce in our stochastic calculations. So remember now that we are evaluating the expectation value of the energy by computing an integral stochastically. Now, what Flyvbjerg and Petersen did was a slightly different rewrite from the one which I did. So where they define this function gamma ij, which is their covariance. And then they measure this, as we also discussed previously, in terms of the distance between two observations, I and j. And the hope then is that this quantity, which you see here, goes to 0 when this distance ij reaches a certain value. So that means this t quantity, which you see here. Now, that what they did, and this is just a result which I restated here, they rewrote the total variance in terms of the sample variance as we defined. And this is the quantity which is given by just a single loop and is the one which we normally have evaluated. And then we have the covariance here. And what they actually have is a recipe by which we can evaluate this quantity without doing a double loop, period. And what they did then was simply to take the data set and transform it into half as large data sets. One thing which is important is actually this does not change the variance and it does not change the mean value. So this quantity should be conserved. However, by this smart way of rewriting it, we can actually find a recursive relation which allows us to calculate a double sum by simply evaluating a single sum. So let's show this first for a very simple case. So let's take a data set which has only 6 observations. And we are going to make these observations extremely simple. These are the data sets which we have. And the observations are, these are like the stupid passwords, which you have 1, 2, 3, 4, 5, 6. Very exciting data set. And we know that when we calculate the mean value, mu here, for this data set, this is obviously 1 divided by 6, and then a sum from 1 to 6. I hope you don't get offended by this simple case here. And when I then perform the calculation, this is 7 divided by 2. Now, if I now calculate the transform data set, so what I would do next is to set up a new data set, x prime, which is now going to contain xi, x1 plus x2 divided by 2. And then I have x3 plus x4 divided by 2. And then I have x5 plus x6 divided by 2 here. So that's my new data set. I have just divided by a half. And I've used this recipe, which you see here. So where did I put that one? Yeah, we put it up here. So I just redefined a new data set, which contains half the entries, but it now is given by the previous entries added and divided by 2. So if I now calculate the mean value with this new data set, mu prime, you will see that you get the same mean value. So it's going to be 1/3, and I just leave that as a small exercise to you guys, of this xi prime, and you will get exactly 7 divided by 2 here. Now, what we could do next is to calculate sigma squared for mu, so the full data set. And in that case, what we have is 1 divided by 6. And again, I don't hope you get offended if I just rewrite these terms here. And this is minus mu squared. So that's the definition of the variance. And if we do the calculations, this should be 8 divided by 3. Then I can calculate the new variance, sigma prime squared, with mu prime. And that is given by 1 divided by 3. And then I have an I equal 1 to 3 here. And then I have an x of I times 2i minus 1, plus 2i here, divided by 2 squared. Actually, this should be squared. And minus this mu prime squared. And that means that what you get then is 1/3. And then I have x1 plus x2 squared divided by 4, plus x3 plus x4 squared divided by 4, plus x5 plus x6 squared divided by 4, minus this mu prime squared. And if I do the mathematics, this is equal to 8 divided by 3. So that means that mu is equal to mu prime, as it should, because we're just making a transformation of the data set. So a transformation and a rewrite of the data set should not change expectation values. So, and this simple example shows you that this is the case. So what we have now is a sigma mu is also equal to sigma prime mu of mu prime. So this is a data set where we split everything in 2 here. Now, what you also see now is that this data set, we cannot do a further split by 2. And this is why it's convenient to have the number of Monte Carlo cycles, MCS, which is given to 2 to the power of some number p here. Because then you can continue to make this split in 2. So you will get blocks which are containing less and less data. And the hope is that these data sets are at a certain point less and less correlated. So what we do now is the following. When we are setting up this calculational scheme, so we are going to have an xi prime. We have a gamma ij prime, which we want to be equal to gamma 0 prime. And what Flyvbjerg and Petersen did was to find a simple recipe for this, so that, and when we start actually with the initial value, then we have xi, so this is where we start. This is where we end after some number of iterations. And we start with this gamma ij, which is simply equal to this term gamma of t. That's where we will start. And we will start also with a gamma 0, which is the same as this sigma squared, as we defined it, which is a simple sum over just the number of experiments which we have. So this is something which is easy to evaluate, and that is a quantity which we have been evaluating all the time. So the whole recipe now is that we want to evaluate this quantity, which is a single loop instead of a double loop. And what Flyvbjerg and Petersen showed then is that this gamma of t prime is given by, when we perform the set of iterations, is given by 1/2 of gamma 0 plus 1/2 of gamma 1 when t is equal to 0. So that would be the first estimation of the standard deviation, where we actually calculate a gamma 1 here. So gamma 1 means that we have split the data set in a half. Then you get a recursive relation, and I'm not going to derive that one, but this is the one which they put up in the paper, plus 1/2 of gamma of t times 2 here, plus 1 divided by 4 of gamma of 2t plus 1, when this variable t is larger than 0. And the quantity which is being evaluated every time now is gamma 0 prime, which is equal to 1/2 of gamma 0 plus 1/2 of gamma 1. So in the first iteration, we evaluate that one, and then we continue to evaluate that one with better and better estimates for this gamma of t. So this is where we would start. And you could continue splitting the data into halves. So this is where we would start. So this is after we have calculated gamma 0, which is the first calculation, which is now equal to sigma squared. And this is divided by n, the number of observations we have. So we would then continue to split the data in halves till this quantity, till this gamma of t reduces to a constant value. Constant value after t iterations. So each iteration is evaluated by calculating a single sum, but where the quantities which we plug in are given now by the equations which you see here when t is equal to 0, and these quantities here when t is not equal to 0. And what Flyberg and Petersen showed is that this converges actually to the correct value. So what you would see then is something like this. So you can actually implement this algorithm directly. So we would now have a t, which is the number of blocks we have. So when we start with the 0 here, this is the point which is called gamma 0 in their notation, which in our notation is the same as sigma squared divided by n. So this is where we would start. And then we go to gamma 0 prime. And this is now given by 1 here. So we have t equal to 1. And in that case, we are evaluating this point here, which is given by 1/2 of gamma 0 plus 1/2 of gamma 1. And that gives us a new point. And then we would continue with these operations till this quantity here now stabilizes and flattens out. Now, what the Flyberg and Petersen did was actually to evaluate. So this is our sigma of m squared. What they did was to evaluate this by the eye. So you made the plots, and then you looked at where this quantity stabilized. In a certain way, this is not that satisfactory. So let's just keep rewriting here. So this would be the new data set, which is the x1, x2, up to xn prime. And where n prime is equal to 1/2 of n. Then this new data set you have here, that will be given by x1 double prime, x2 double prime, up to xn double prime. This is double primed here. And then this n double prime is actually equal to 1/2 of n prime. And I would continue building up this. And I invite you to take a look at the simple model, which we put up here, these observations. And you would see then that the standard deviation and the variance, they are conserved for every time we perform this kind of division by 2 here. So the quantities have to be conserved. And what happens then is that we have a recipe where we now evaluate the variance in terms of this gamma 0, which is just given by a single loop. So we have a single loop in the evaluation here every time. And that's the benefit of the method by this splitting in 2 continuously, that we all the time we just evaluate a single loop over the variances. And you can then show that this converges towards the desired value if you were to calculate the full covariance. So I invite you to play around a little bit with the algorithm. If you wish to, you can easily set up a data set with, let's say, 1,000 points and calculate the exact covariance, and then compare that with what you would get from the blocking method by slowly performing this calculation of gamma 0 prime, gamma 0 double prime, etc., etc., etc. And at the end, this should converge towards the correct value. So I'm not going to go through the derivation of these expressions here, but you can then just think of these as expressions which are obtained by simply rewriting the covariance term. Okay, so what I want to do now is to go back a little bit to the slides and discuss how you can implement this method and the kind of the strategies which we should use in the calculation of expectation values. And I'm going to use that program example, which I've been using throughout the semester. So let's switch back to the Jupyter notebook here and take a quick look at how we can implement this. And I recommend, if you want to, and also that will save you times, is basically to use the codes which Marius actually developed. And these are the codes which I've taken and implemented in this implementation here. So the whole idea is that first we run a Monte Carlo calculation, a variational Monte Carlo calculation, where we produce lots of data which we save to file. So if you're running this in parallel, you will simply save your Monte Carlo cycles to file. You may not need to save all the data. So many practitioners, what they end up doing is, suppose you run 1 billion Monte Carlo cycles, you could save every 100th observation of the energy, or every 1,000th observation of the energy, and treat those as the data you want to plug into a resampling technique. So also by doing that, there is a lot of kind of practitioner's experience where people often have seen that after a given number of correlations on given number of samples, the distance between different observations, that the results are almost independent of each other. So for the type of calculations we are doing with the harmonic oscillator, you would see that you would need something between 100 to 1,000 observations or Monte Carlo cycles in order to see something like a covariance which is going to 0. So in the examples which I have below here, I'm actually calculating and writing to file all the data I have. So if we scroll down after we've gone through some of the mathematics here, and I'm coming back to some of these calculations because you can, with the covariance, you can actually define something which is the correlation time, and which is a measure of how long you need to run, or what is the distance between Monte Carlo cycles, and when you can decide whether you have reached a result where the results are basically uncorrelated, which means that you can treat every observation as a stochastically independent observation. And normally this requires some simulation time. The reason why you normally don't evaluate this correlation time is actually this means evaluating the autocorrelation function, which again is a double sum. And you don't want to do that. So the autocorrelation function is useful to calculate for few samples, but it's normally never used because it's too time consuming. But it can give a useful insight about the problem. But as I said, I mean, it involves you having to evaluate a double sum here. So this is normally not implemented in calculations. And often what is implemented in the calculation is a practitioner's experience for the type of calculation you're dealing with, and when you expect that the results will be basically uncorrelated. So if we go back to the resampling techniques, I'm not going to discuss the Bootstrap because many of you have seen that before. And you can just look it up here. The thing which is nice, what I've done here, just as a simple example, is a demonstration of the central limit theorem. So I produce a bootstrapped result where I start with a distribution, which is a normal distribution with a mean value of 100 and a standard deviation sigma, which is 15. And then I generate 10,000 data points. And in the function which you see here, what I'm doing now is simply to reshuffle these points by this randint function, where I now take the observation I have, and that produces a new data set. And that new data set is now simply a reshuffled data set. And this reshuffled data set simply is used then to calculate a new mean value and a new standard deviation. So I produce 10,000 new data sets. So in total, I'm producing 10,000 times 10,000 observations. And what you would see then when you run this calculation is something like this. So this is the original one. Now I don't get exactly 100 because I have only 10,000 data points. So, and if I rerun this now with 100,000 instead of 10,000, I will get a result which should get closer to 100. Now, what I've done here is now to perform 10,000 new experiments. And this gives me a standard deviation and a distribution, which so the mean value shouldn't be changed. But now I've done 10,000 new experiments. So my standard deviation should now be given by this 15 divided by the square root of 10,000, which is 100. And you see, I produce a normal distribution. It looks like a normal distribution. This is where I plotted the normal distribution. Due to the fact that I have only 10,000 observations, then I clearly won't get a perfect reproduction of a normal distribution. If I were to increase this to 100,000 and perform 100,000 resamplings, then clearly what I would get would be a data set and histograms here, which are closer to the exact normal distribution, which I would like to simulate. However, I would use much more simulation time. So if I were to run this with 100,000 instead, you would quickly see that this is going to take much more time. So previously it took just a few seconds, but now this is running over longer times. And you see clearly that when you increase the data set here, the size of the data set, then a method like the Bootstrap as a post-analysis method becomes much more time-consuming than methods like the blocking method. So you see this is still running here. And it's going to take a little bit more time before we actually have some results. So the reason why I did this is not only because I want an ISA histogram, but also to demonstrate that even if the Bootstrap method is very efficient in ways to resample the data set, it becomes time-consuming when I have much more data. So if we just wait a little bit more time here, it should come up. That gives me the possibility to take a sip of my coffee here. But probably we will have to wait a little bit longer. So I'm coming back to these results. So this contains just a description of the blocking method. And what I have plugged in here, so this is just a repeat of what we did on the whiteboard. And with the final expressions for the blocking method, the way we would implement them. By the way, here we have. So this time, in the previous case with 10,000 data points and 10,000 resamplings, I used 1.2 seconds, and now I used 81 seconds. And actually, I would have had to change the units a little bit. along the y-axis, because this is much sharper now. And with more data points, I'm getting closer to 100 for the mean values. And you see that the mean values are conserved, obviously, as they should. And the curve is much sharper, concentrated around the mean value. So what I'm producing now with the Bootstrap is now a better distribution of the data points. It's a normal distribution. It has a changed variance, which now follows the number of experiments which we have, which is this original sample variance divided by the number of experiments. Okay, so let's now continue here and go down and take a look at the blocking method. And this is based actually on Mario's master thesis, which was published as a scientific article afterwards. So what I have here is a calculation of this 2-electron case, where I use this method by Broyden, Fletcher, Goldfarb, Shano, which we discussed the week before the previous week. And this is a quasi-Newton method where we try to estimate the second derivative without actually calculating it. And the search directions are then optimized by looking at the gradients. And in this case, we have the same program which we have seen before. It's a 2-electron case. The trial wave function contains the harmonic oscillator in 2 dimensions. So it's pretty similar to what we have in project 1, but then the correlated wave function is slightly different. And this correlated wave function contains then a correlation which is meant to cancel the divergency in the Coulomb interaction when 2 particles are getting close to each other. So when the interparticle distance goes to 0, we have a divergence, and that divergence is cancelled by a divergence in the 2-electron kinetic energy, and that puts a constraint on the form of the wave function, which is what I plugged in here. So I have analytical expressions for the wave functions. I have analytical expressions for the local energy. I have a analytical expression for the derivatives of the wave functions, which I'm using to calculate the expectation values of the energy and also the expectation values of the derivative of the energy with respect to the variational parameters. In this case, I have 2 variational parameters, alpha and beta. So it's the same example which I've been using again and again in the course here. And it's pretty similar to project 1 for the non-interacting case, except that now the interacting case is due to the Coulomb interaction or repulsion between 2 electrons. I calculate this quantum force. I have a function to calculate the derivative of the energy, as we discussed previously. And this is unchanged from what we have before. I calculate the energy here. So this is also unchanged. I have importance sampling, etc., etc. The only thing now is that I have a printout statement. So I actually write out my expectation value of the energy after a given number of Monte Carlo cycles. And I do this for every Monte Carlo cycle. So you could choose here in this printout to change this to, let's say, every 100 Monte Carlo cycle, in case you have many data, because if you have 1 billion Monte Carlo cycles, you're writing out 1 billion expectation values of the energies. So these are my expectation values as I progress through my Monte Carlo calculation. You do often have a burn-in time, which I have been sloppy with here. So the burn-in time is actually the time you need to reach the equilibrium situation, which means that you have a steady state, and then you're just collecting data around this steady state, which is the optimal state. So remember that the Markov chain converges to the steady state after a given number of iterations. And then when it has converged, you're simply fluctuating around that steady state, and that's where you collect data. So this correlation function, which I mentioned earlier, has often been used to find how large this burn-in time is. But there are many strategies, because calculating this correlation time was okay if you had few Monte Carlo cycles. but nowadays you can actually run billions of Monte Carlo cycles. And the kind of strategies then is to say that this burn-in time before you reach the steady state is so small compared to these billions of cycles that these just disappear in the big machinery, and that you can basically neglect the fluctuations, the larger fluctuations you had before you reach the steady state. Alternatively, some people from experience, they would say that, okay, let's skip the first 10% Monte Carlo cycles because that's what we typically need to reach the steady state. And in this case here, I haven't cared to do that and simply just run through it, because I often see that with importance sampling, I reach rather quickly the steady state. But this is something, if you want to write a more professional code, you should think of bringing that in. So what I do here is simply now to start the parameter optimization. So I'm running 100,000 Monte Carlo cycles first, and then I use that one to calculate the gradients and find the optimal parameters. So when I'm done with that, I have now found the optimal parameters here, which are obtained by Broyden's method. I have only 2 parameters, so this is a pretty easy function to optimize. I need to plug in the energy function and the derivative in order to use this function from SciPy, which is called minimize. When I'm done with that, I'm going simply to run my large Monte Carlo calculation. And then I have a printout true, and I calculate my final energy by simply now rerunning everything. And that writes to file the final energy and in an array here. And then this file is the one which I then include in the calculations afterwards. And what you will see here now is the optimization I get and the optimal parameters. So these are the parameters which I'm going to use in the final calculation. So this is one parameter, and this is the other parameter. This is my final energy. The exact values is 3.0. But you see now I don't have an estimate for the error. So this is just the expectation value of the energy. Now, since I print out all these results here to file, then I can now use the codes which you will find available at the website of the course here, and which then produce the optimization here. So what we have is a sampling functions, which you then can use for the post-analysis. And this is a kind of strategy which I would recommend using here. So this result is actually pretty close to the exact result. And if I were to increase the number of Monte Carlo cycles here, I could get a result which is getting closer and closer. But still, since I don't have the exact wave function, I wouldn't be able to get the exact result. But I'm getting pretty close, which is not bad, with a very simple answer for the wave function and only 2 parameters. Then the way we proceed now is simply to take this data. So this is the file which I called energies data, which now simply write out here. I just write out the energies. In my case, I've set up an array with the final results here and just simply print it out. And this is what is done here. And if you go and look into the folder which contains this data, when you run the code, you will find this specific file here, which simply contains the observations, the values of the energies. And then you can perform a standard boosting calculation. And this is what boosting gives us. So it has an original value here. Actually change the data a little bit in these runs. And it calculates the standard deviation, which is now a standard deviation which assumes that I actually have a very simple, how to say, independent and identically distributed elements. So this standard deviation here is a little bit too optimistic. When I then use the blocking method, and if we go down here, so the mean value is now conserved, should be the same as I had with blocking, now with boosting, but this is now the standard deviation, which is evaluated by the blocking method. And these are the results which we should present. So when we present the results, it should be 0.7 something plus minus the standard deviation, which you see here. So I would recommend using the codes which Marius has provided in his article. There's a link to the scientific article which he wrote. So this is actually one of the beautiful things with this course here, that often people they come up with ideas and sometimes it ends up in a scientific article. In Marius' case, this was actually an article in the Physical Review E. And if you click on this link here, you will actually get to the scientific article. And this is actually based on an idea which he got while he was following these lectures. And I was presenting Flyvbjerg and Peterson's method. And he was unhappy, not very satisfied with the proof. And he had just improved the proof here, actually. So this is a thing which is often nice when you teach courses at this level, is that there's always somebody who cooks up something new. So this is a direct result of, so Marius took this course in 2017, and I just went through Flyvbjerg and Peterson's method. He had a background in statistics, and then saw how he could improve the method. This is pretty neat, isn't it? That's what we often want to, or it's a kind of ideal when you teach, that one can actually improve upon the teaching material by adding better codes, because Flyvbjerg and Peterson, the way they actually implemented the method was calculating the standard variance by the eye. So when the results flattened out, they would say, okay, we have reached the right sizes of the blocks, which tells us that we have basically independent and identically distributed stochastic events. Okay, so I wanted just to end today's session with a discussion of a quantity which we normally produce in these projects, and that's called the one-body density. And let us just set up some of the mathematics behind the one-body density, and then we are going to be done for the day. Next week we are going to look at how we can parallelize these codes, and then we will also wrap up the project. So you will find, if you're a little bit impatient, you can find the material about parallelization for the weekly slides for next week. But let me say something about the one-body densities, and then we're going to conclude today's lecture with that. Because that's a very fine quantity which can be used to evaluate the degrees of correlations. So let's just write this down. One-body densities. This is a small technicality, but it's a very interesting technicality. So the overarching aim is to understand the role of the interaction. So the idea here is to unravel information about correlations. With that, what we mean is actually to be able to calculate quantities, in this case expectation values, which can be used to extract information about the role of the interaction. So the one-body density is a quantity which then tells you how particles are distributed. And the way you would calculate this quantity, suppose now you pick particle 1, but you can actually put, instead of putting R1, you could actually write a general R. So this quantity is given by the expectation value over all the other particles. So you don't have particle 1, but you have all the other ones up to dr of n. So this is a typical calculation you would run after you have optimized your wave function. And this is then multiplied with, and then you have your trial wave function with the optimal parameters. So now you have all the numbers here, all the positions. And this now contains alpha hat and I put a vector sign to indicate that this is actually an array of different operational parameters. In our case, in project 1, we have just one. So the hat here is the optimal one. So that means that this is the calculation you would run after the optimization. So you wouldn't perform this calculation here before you have optimized it. So when you found the optimum parameters, then you have the wave function. And then you would simply use that one to calculate these expectation values. Now, in our case, we are in either 1, 2, or 3 dimensions. So if you now think of you being in 2 dimensions, just as an example, then what you're going to do then is to let this R1, we're going over to spherical coordinates, and we're going to let this R1, sorry, let me just rewrite it so it looks, my letter R looks always bad. So this is given by x1 squared plus y1 squared. If you are in 2 dimensions, if you're in 3 dimensions, you have z as well. So what you would make then is a table. So make a table. And the state which we are going to look at is the ground state, which means that we have no angle dependence in our case. So there is no angle dependence in the wave function, phi dependence. So if you just, so this is just switching to polar coordinates. And if you do this in 3 dimensions, you would have spherical coordinates. And there as well, for the lowest lying state, which is isotropic in space, we have no angle dependence. So that means that we can integrate out the degrees of freedom coming from the angles. And in 2 dimensions, this gives us a factor of 2 times pi. If we are in 3 dimensions, this gives us a factor of 4 times pi. I guess you're familiar with these kind of expressions. So what we would make then is a table. So we are setting up a grid with values x1 and y1. So we would simply then calculate x1 and y1. So we set up such a table, and this is going to give us R1, row of R1, by simply squaring these 2 quantities. So what we would plot then would be something like this, and this is the way this could look like. So we would then plot it as a function of R1, and we can just take away the R1 subscript and just write it as a R. But now let's stick with R1. You would get the same result for R2, R3, and so on, because the wave function, just keep this in mind, has the correct symmetry. So that means whether you interchange particle 1 and 2, you should get the same result when you perform this integration. So in principle, we could just let this go over to a variable R, and then we could simply have rho R. So what this is showing us is the distribution of a particle. And this could look something like this, just to give you an example. Now, the thing which is interesting for us is the role of the interaction. So let's suppose now that we look at the results with an interaction. So let's suppose that this is a calculation we have run with no 2-particle interaction. So what you need to do now is you set up a grid of values. So you could let x1 go from -1 to +1, for instance, and the same with the y1. And with these values, you have the values for r, which are just given by the square root of x1 squared plus y1 squared. So you would have this table. If you're in 1 dimension, you just need 1 variable. If you're in 3 dimensions, you will need x1, y1, and z1. And the thing now is that suppose this is the result with no interaction. Then what I can do next is to add the calculations I have with an interaction. So I could think now of a repulsive interaction. Then perhaps my results are going to look like this. I may get something which goes like that, for instance, because this is now repulsive, and that means that the particles get pushed out. So pushed out from the origin. The next thing I could do now is to have an interaction which is attractive. And then clearly, if I do that, what I will see is something like this. So I will get an interaction then on a density here, which looks like this. So that means that's pushed in, or pulled in would be better, actually. So that would be the better verb here. So this would be pulled in. So if you have the non-interacting case as your reference frame, then you can see the role of the interaction. If these one-body densities differ a lot from the non-interacting case, then what happens then is that you would say that my interaction plays a very important role. Now, the one-body densities can actually be related to observables. So for charged particles, you can study experimentally something which is called the charge distribution. Now, remember that these quantities are not true observables, but you can extract information about the charge distribution from experiment. And then you can relate this experimental charge distribution with the single particle distribution here. And then if the non-interacting case is close to what you extract from experiment, then you would say that this is a system with small correlations, that the interaction doesn't affect the motion of the particle beyond some small effects which perturb the non-interacting case. If you, on the other hand, see a large difference, then you would clearly state that the interaction plays an important role if I assume this and this single particle basis. So remember also that when you calculate the non-interacting case, that will depend on the ansatz you have for the single particle basis. So you may not have the correct single or the best single particle basis. There is nothing like the correct single particle basis. The better statement is the optimal single particle basis, which represents the data. So remember now that the wave function is not an observable, and everything we are making are models. However, with a one-body density, you can then say something starting with your harmonic oscillator basis, how important the interaction is. And if the interaction is very important and you see a large change here, maybe you should rethink your single particle basis, which is used to construct the wave function. So this kind of back and forth is used in your analysis of the wave function. And the one-body density is one of these measures, which tells you how different the final wave function is from the non-interacting case. And that gives you some information about the role of correlations, which are induced by the interactions. Okay, this stops today's lecture. I'm going to upload this quickly online so that those of you who could not be here can actually revisit the video. And then we have the lab, which today begins at 2:15 here.